Hi, it's Griffin, and we're going to work on making a tank drive subsystem. Last time you kind of learned what command-based was all about and how the file structure generally works, but over the next two videos, we're going to show how to convert what you did in robot.java with the tank drive into a subsystem in command format. So the first thing to do in a fresh command-based project is to delete some of the default files if you created a example one. You'll see it as an example subsystem, autos, example command. Let's just get rid of those. You're going to click the delete key and move to recycle bin. And then you'll see some errors pop up in robot container. Delete anything that has errors, like this. And then for the get autonomous command, for now we won't be running autonomous, so we're just going to return null. Do know that this could cause your code to crash if you actually run it like this, but we're only simulating and we're only doing teleop for now, so that shouldn't be a problem. Additionally, we're going to comment out this command Xbox controller for now. We'll come back to this later. Alright, so now your project's a lot more of a clean slate. The first thing we need to do, of course, is create the subsystem. The way you do that is you go to the appropriate folder you want to create it in and right-click. There, among the normal file options, you will see an option to create a new class in command when you're running in WPIlib VS Code. You click on this, it pulls up a upper console, and you can just type in subsystem. You can see that comes up with the option for a robot subsystem. We're going to select that. Now we need to name it. Let's call it tank drive subsystem. Look at that. Creates a new file, imports subsystem based, sets it up with its periodic function, which runs every 20 milliseconds, just like teleop periodic or robot periodic. It also sets you up with a constructor. So now we have our subsystem, but what do we actually want to put inside of it? So remember, a subsystem generally represents a physical part of your robot. So the tank drive subsystem represents the physical parts involved in the tank drive. That would be your driving motors. So the first things we're going to add to this file are the motors. Starting from the top, just like how we instantiate our motors in robot.java, we are going to add private Talon FXs. Remember to hit enter to import it. We're going to go with the same 4-motor configuration we did before, a left primary and follower, and then a right primary and follower. Let's start with the left side. So we got a left primary, and we're going to instantiate it right here in this line, just like we did before. Goes new Talon FX. But now we need a device ID. So you could just type in the device IDs right here that you grabbed from Phoenix Tuner, but a better way to organize your code is to store these in constants in case you ever want to change locations, or so that you can be more confident that you don't mistype a number. Let's delete this and save the file for now. We'll come back here in a little bit. So we're going to delve into a new file, constants.java. This is where you can store, well, constant stuff that is always true about the robot. This is usually used for configuration stuff. The way that constants is usually formatted is by having subclasses like they have an example here. So for our tank drive, we're going to create a class inside of the constants class named public static class tank drive constants. Now inside of this, we can store our constant variables. So let's make a public static final int left primary ID. And let's say this is 1. Let's say we went into Phoenix Tuner and ID'd it, and this came out as 1. While we're here, let's put in the IDs for the rest of our motors. We're going to have a public static final int left follower ID. So let's say is 2. Next up, let's move this on down and create our right side. Copy it to make it a little quicker. Cool thing you could do in VS Code, if you hold down your middle mouse button and highlight, you can have a duplicate cursor here, which edits 2 lines at once. So I'm going to delete all these, type right. And then for the numbers, these are going to be different. Let's say right primary is 3, right follower is 4. Now whenever you're copying stuff, do a double check that everything looks good. Left primary, left follower, right primary, right follower, no motor IDs or duplicates. Perfect. Let's go back to tank drive subsystem. So now to obtain this constant, you can just type in right here, tank drive constants, and look, it has a suggestion for what to use. Hit enter and it'll automatically import it from constants. And now we need to actually grab the variable from inside of that tank drive constants class. Do that by using dot left primary ID. Perfect. Let's move on to the left follower and copy this line to make it a little easier. Now this is our left follower, and it should have left follower ID. Moving on down, we're going to do our right motors now, which is going to be a private talon FX right primary. It's just going to be new talon FX device ID tank drive constants dot right primary. Private talon FX right follower equals new talon FX tank drive constants dot right follower. You get the gist. Pretty copy and paste, very similar format. This just makes stuff more organized. Alright, let's move on to our constructor. So in robot.java, we usually configured our motors inside of robot init, but in the subsystem model, subsystems are instantiated right upon the running of the robot code. So you can do all your configuring in the constructor, since these are run with the creation of your subsystems. Starting off here, we're going to use the same exact access to the configurator as before. Starting with left primary, we're going to get its configurator, and then we're going to apply a config. Now, for this config, yet again, instead of typing it out multiple times across all these lines, we're going to put it in constants. Inside of our tank drive constants, we're going to create a public static final. And by the way, I didn't mention this earlier, but all this is saying is that public, it can be accessed by anything that can access tank drive constants. Static, meaning that you don't have to create a tank drive constants object to access it. And final, meaning that this cannot be changed after the code is run, because you should never have a change in constant. Anyway, the type of the object we want here is a talon FX configuration, which is usually what we apply to the motors anyway. We're just going to call it configs, and we're going to set it equal to a new talon FX configuration, just like we did before. Now, if you want to add some special configurations, you can use a dot, and then there's a bunch of with options, which allow you to apply different configurations, but that's not a concern for now. Going back to our tank drive subsystem, we're going to apply this config. So we can access tank drive constants again. Then we're going to do .configs. Perfect. Let's copy this line down a couple times for us to edit. Remember to be careful of copying stuff like this and make sure everything matches. So we're going to have a left follower. And then we're going to have a right primary. And then we're going to have right follower. They all have the same configs just like we did before. But now it's all the same object, so if we change it right here, we add a dot with and then some sort of change to the configuration. All of the motors are going to have it right here instead of having to go one by one and changing it. Great. Next up, you got to apply your current limits. Remember, no forgetting about your current limits. So to save some space and make our applications of current limits a little bit quicker, we're going to make a helper method for it. We're going to create a public void apply current limits. All this is going to do is help us then we don't have all the current limit application stuff inside the constructor. Formats everything a little nicer, easier to look through your code, generally suggested. So the first thing we're going to do is we're going to create a local current limit configs object, and we're just going to call it current configs. And we're going to set it equal to another constant. Let's go back here. You should know the drill by now. Public static final. This time it's going to be a current limit configs. We're going to call it current limits. We're going to set it equal to a new current limit configs. And now we're actually going to use the dot with syntax. Now when I write my code, I like to do the dot width on the next line so that you don't have one line extending all the way off the side of the screen. So what you can do is you can just hit enter, press a couple tabs, and then because in Java this line still extends until it's terminated, we can just add a dot width. Then we're going to do a state or current limit of 80 like before. And then we're going to add another dot width, current limit enable true. So that's telling it state or current limit 80, state or current limit should be enabled. Moving along, let's go back to the tank drive subsystem and use that new constant we made. Tank drive constants again. This time we're going to do dot current limits. Perfect. Now, like we did before, we're going to refresh the config. Getting the configurator, using the dot refresh, then we're going to refresh current configs. We're going to refresh it on every motor, so copy and pasting again. Left primary, left follower, right primary, right follower. Great. All the motors covered. Now we have to go through and actually apply the configs. So let's type in our motors again. Left primary dot get configurator dot apply current configs. Go through and do that for all the motors. Gonna do a bit of copy and pasting again. Make our life a little easier. You got our left follower. You got our right primary. And we got our right follower. Checking through, left primary, left follower, right primary, right follower, perfect. And we have them all applying with the same current limit configs. Great, now let's make sure to call this method inside of our constructor so it gets run when we configure our motors. Dot apply current limits. Awesome. Yet again, like we did before, one of the sides is going to need to be inverted. Let's choose the right side to be inverted. On a real robot, yet again, you would actually be testing and seeing which side should be inverted to get the movement that you want. But here, we're just going to pretend that we checked that and the right side needs to be inverted. So we're going to invert the right side. Last but not least, we got to set up those followers. So let's go to the left follower and set its control to be a new follower of ID. Here's where the constants come in handy. Tank drive constants dot left primary motor, and it should not oppose the master direction. So the left follower should be following the left primary. Yet again, constants are really useful here. Let's say you end up changing the ID of the motor. If you don't have constants, you might forget to change this one or this one. With one constant, the variable is saved in one central location. I'm going to copy this line set up for the right motors. So we got our right follower setting its control to follow the right primary ID. That concludes the basic config. Let's move on to adding some methods. Let's dip on below the current limits, create ourselves a little bit of space, and we're going to create the drive method. Now, before, when we wanted to control our motor, we would take the input we wanted, like for example the joystick, and just pass it directly into the motors.set method. But with the subsystem command model, it works a little bit differently. We have one method inside of this tank drive subsystem that receives the inputs and then does the setting. This allows more modularity with commands overall. You can run different types of drives at different times, not have to be worried about a whole lot of if statement logic. It might seem like a lot of work now, but trust me, as a robot project gets more complex, it is almost a requirement. Let's make our public void drive method. Now, before, we passed in a certain % out to the left motor and a certain % out to the right motor. We're going to do the same exact thing here, but we're going to receive them in this method. So we're going to take in a double left % and a double right %. Now inside the body of this method, we're going to use those percents and set it onto the motors. So we're going to take our left primary, use .set to the left %. Then we're going to use our right primary and set it to the right %. Great. So now if you passed in joystick inputs to this, it would run just like we did before. Now the other method we're going to create that can be handy in certain scenarios is a public void stop. Stop all the motor activity. It It's a little more explicit than just giving it a percent of 0 and 0. Talon motors actually have a built-in method to help with this. So if we do left primary, we can actually use .stop motor. An important thing to note about stop motor is that you should only stop the primaries, or else if you stop the followers and then you try to drive again, the followers will lose their followership status. So just take the primaries and stop them. The same goes for setting. You shouldn't be setting to the followers. So now that we have our functional methods going, the things that actually change the robot's behavior, let's make some helper methods to get some important data about these motors. Adding these methods can help make shuffleboard printouts easier. Let's make some getters for the percent outs of the left primary and right primary motors. So let's make a public double get percent out left. This is just going to return left primary dot get. Now you might be asking, why go through the effort of doing this when you could just run left primary dot get? Well, sometime you might need to access the left's percent out in a file that is not tank drive subsystem, and remember, these motors are private, so they wouldn't be able to be accessed. Another thing is that it keeps your code a little cleaner to have these getters that are explicitly defined. We're going to copy this, then we can easily make one for the right, being careful to change our right here and our right here. Copy and pasting is efficient, but if you mess it up, it can confuse you and waste a lot of time. Now, to demo these percent out getters, let's use a smart dashboard printout in periodic. Remember, periodic here functions just as your robot periodic did, but it's within the subsystem, which can keep you a lot more organized, since now you can choose what you want to be printing out or what you want to be doing on a subsystem by subsystem basis instead of sticking it all in one method. Right here, we're going to do smart dashboard.put number with the key left percent out, and we're going to use get percent out left as it auto-corrected right here. Copying this over. Let's make one for the right. Using get percent out right and key talk about the right. Now we have a basic tank drive subsystem laid out. There's one more thing to do. We need to actually instantiate the subsystem. So where do we do it again? Robot container. Robot container should house, well, your robot. As this handy dandy comment suggests, let's put our subsystem at the top. Let's make it private, and we're going to create a new tank drive subsystem object. Remember, that's what we just assigned right here. Hitting enter imports it, and we're just going to name it here tank drive subsystem using some camel case right here. Now we need to actually instantiate it. New tank drive subsystem. Perfect. As soon as this tank drive subsystem is instantiated, the constructor is called, meaning your configurations are going to start, and then its periodic starts getting scheduled to run every scheduler loop, which means every 20 milliseconds. You might be asking, where's robot container called? Well, that's back in robot init of robot.java. So you can see how it comes full circle, functionally gets called at the same time as it did in our robot.java model. But now everything's a lot more organized. Now, one note that I wanted to add in is that this tank drive subsystem object that you just created here with this new tank drive subsystem call should be the only tank drive subsystem object throughout your whole code base. You shouldn't be going into robot.java and creating a new tank drive subsystem. You shouldn't be going to constants. You shouldn't go anywhere, not in a command. This should be your one tank drive subsystem. Anything that needs a tank drive subsystem to run, for example, some sort of command that needs to utilize drive to control the robot's motion, should be using the same object, which means should be having this exact tank drive subsystem object passed in as an argument. So remember, this should be the only time you're writing new tank drive subsystem. Let's do a quick simulation and see if we get those smart dashboard printouts. Sim GUI and driver station GUI. So on the screen, I've got our simulation data. You'll see, look, on our smart dashboard, we got our printouts for left percent and right percent. Of course, they're 0 right now. The robot's disabled. And we haven't actually called the drive method anywhere to command the motors to do otherwise. You can also see inside the robot simulation tab we have motors 1, 2, 3, and 4, so they were all instantiated correctly. This is how to create a basic subsystem. It's not going to do much yet, but in the next video we'll show you how to make a command so that you can actually control it.